I'm Evelyn Boettcher. I work in own didactics. And today I'm going to talk about processing large data with Python Pandas. And this talk was, I think I was motivated by the fact that I had at work, suddenly I went from like reading a couple of, hundreds of thousands of lines of code and, 10 columns to being sat in front of a computer with only 16 gigabytes RAM. And now I have tens of millions of lines and 50 columns. I had to process all that data and pull it into it. So how can you do that? And I've learned with using pandas, and particularly using categories, I was able to reduce the in-memory footprint by 90%. So I was able to then pull that data and process it.
Primarily in a Linux environment, or?
This was on a Windows machine.
Okay. Well,
I would have
the reason I'm asking is that I've been following some people trying to deal with the modern desktop systems with multiple processor cores. And Windows apparently is moderately good about providing an environment where it can distribute.
Oh, Windows was horrible. Windows, if you do threading in Windows, it will copy each data into each thread instead of having it globally. And so if you wanted to process large data on Windows, even if you had only a gigabyte in memory, if you do 8 threads, that's 8 gigabytes now, and then your program just goes, whoop. Well, on Linux, it doesn't copy it, so it's very smart. But that's what not this talk is about.
Yeah, there's different ways that they're approached, and given the monstrous caching that can happen on a lot of modern CPUs.
Well, this is a Linux. I will always go to Linux unless I'm forced to by my customer to work on Windows.
Mostly I do scripting things in Windows, which is not cheap, but after they get started, it's like they run like a real bad out of heck.
But, you may say that your data is really, really big, and this is not my talk, I just need a better computer. Well, you don't always get a choice to get a better computer, so this is what's for you. And large data sets have always existed. So take Johannes Kepler in the 1600s. He worked for Tycho Brahe because Tycho Brahe had the largest data set ever of observations on the planets. And he really wanted to prove, the motion of the planets around the sun. And he could only prove his theory by using Tycho Brahe's observations. Well, Tycho Brahe was a jerk. And he refused to give it, even though Kepler was living with him, the data set. And so he had to wait until Brahe died. And many people think, to this day, that he killed Brahe to get this data set. And Brahe has been exhumed so many times to test to see if he really was murdered or not. And the data sets, 70 years later, Romer, armed with only a pencil, paper, and a telescope and a watch. I mean, in the 1600s, watches were pretty bad. You couldn't, navigate a ship with those watches. He calculated the speed of light within 30% just by looking at the moons of Jupiter. Like, he wanted to predict when Io would have an eclipse. And prior to this, people thought the speed of light was instantaneous. And he was only off by like a couple of minutes, 7 minutes. His calculations and when the eclipse occurred was only by 7 minutes. So if you made some measurements and you're only off by 7%, you might say, okay, I'm good. This is good enough. And he wasn't for him. And so for him to say that it wasn't a mistake in the observations or his math, he would have had to recalculate all this by hand. And he's looking at handwritten notes from all these different scientists over hundreds of years. And then at the end of the day, he's like, my work is correct. It is light that is wrong. It is not instantaneous, but it's finite. You got to admire that confidence in your data. I mean, there is no one that has bigger kahunas than Romer, in my opinion, because to say that the speed, go from the theory that light moves instantaneous to like, no, it's finite. This is its speed. I was like, dude, you're awesome.
His contemporaries all thought it was hubris.
So we have it easier. We really only have to deal with like slow download speeds and nans, not a number. And but you say, ooh, my data's really big. I don't want to wait a decade for my answer. I don't want to have to be accused of murdering someone to get the data. So let's talk about Python Pandas. So Python Pandas is really a high performance, it's easy to use library, and it's for structured data. So if you have CSV files, SQLite, JSON, etc., this is an awesome library to work with. It's fast, powerful, flexible, and enables you to quickly parse data. And it's mainly designed to handle for data sets less than 100 megabytes. But we'll show you how to handle when it's, a gigabyte or more. There are other tools like Spark that handle large data sets. If you have 100 gigabytes, a terabyte, you really need to switch over to these other systems. But if you have, if it's like only a couple of gigabytes and it's messy data. So Pandas really handles a lot of messy data, like things don't quite match up, uppercase, lowercase, strings, mixture of strings and numbers. This is the data set for you. So when you do have some real-world data, and real-world data is always going to be a mess, and you want to explore it, you want to use your laptop, and you don't want to switch to Spark. So how do you handle just really large data? Well, the first step is to use old programming tricks. So you try to reduce the size of your numbers to the smallest possible byte. So see if you can use an int 8, a float 16, a float 32, or et cetera, just to reduce the memory. Because a lot of times when you read in the data sets, it's even for an integer, like an int 8, it's going to read it in as a float 32 or float 64. And that's really big. And you can really drop the size of your data by a factor of 4 or more by just doing this.
Yeah. If you guess like int 8 and it doesn't fit, is Pandas like gentle about erroring? It won't like truncate silently or something, will it?
No, it won't. I don't.
If you carry outside of int 8, does it
if you try to cut down the memory, but you guess wrong and you don't realize that some of your data wants more than that.
It will try. Most of the time, Pandas will automatically update to. So like most of the time, like Python will like upgrade it to what it needs to be. But I would always do I'll just read it in and read that column in and see what the max and minimum are, and then set it to it. And then the second step is to use categories. So you don't always have the luxury of having numbers. A lot of times you want to process strings, and strings tend to repeat a lot of times when you have in a data set. And if the strings are repeating, then you should use categories because that drops the data set down quite a bit. So example of non-repeating strings is if you have a string list and you say, hello world, more strings, Evelyn, Boettcher, none of these are repeating. So doing categories would be a waste because there's overhead to that and it's not giving you anything. But if you have repeating strings, like say you're pulling stock market data, you want to see what's the best day to sell, then you're going to have, Monday, Tuesday, Monday, Wednesday, Monday, Sunday, Sunday, Sunday. Those are repeating strings, and that's when you want to use categories. And this is where the magic of categories is. So in this talk, we'll go over how Pandas uses memory, Python uses memory in Pandas. We're going to reduce the data frame footprint, learn what data types are. So I just talked about some data types like int 8 and 16, char. Those might not, know what those are. And then the speeding up, reading up CSV files, and then finally reduce the memory footprint by 90%. So memory footprint. So a byte is an int 8. So it's usually for numbers from 0 to 255, or if it's signed, minus 128 to 127. Or bools. Bools are actually an int 8. Bytes are like int 16, float 16, and then you got 4 bytes, and then 8 bytes, which is an int 64. And so this is how much data it takes up in memory. So like 1 byte, there is actually 8 zeros or ones in a combination. And then for strings, Python uses 3 different types of Unicode strings. For a Latin encoding, it's 1 byte per character. So if you had Sunday, that's 6 bytes plus the overhead for that string. So that's why strings take up so much more memory. And then if you're using US4, which is 4 bytes, that, you could probably reduce, if you're only using American code on Sunday and it's calling it US4 encoding, just changing the encoding to Latin will reduce the memory by a factor of 4. So how does categories work? So Python categories uses an integer value to map it to the raw column value. And so this mapping is really useful when it came into a limited set of strings. So if I had my data frame, my days, so Sunday, 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 pandas would say Sunday is equal to 1, and then the data frame is the memory expected to like 1, 1, 1. And those are int 8s. So instead of having each character be an int 8, now you have 1 int 8. And that drops the memory by a factor of 6 by doing that. So converting to categories, so to convert a column to category is super easy. You just go on data frame and then the column name dot as type, and then you set it to category.
Does it build those on the fly?
What?
Does it build the category on the fly?
Yes. So if you have more than 256 categories, it's not going to be an int 8, because it's going to map it to something higher. It's going to have 2 bytes.
256 members, or?
Yeah, if there's like 256 members, like 256. But if you have more than that, it's going to map it to, now it's going to be int 16 or int 32. But it's going to be a lot less memory than the full string. And then, but converting to categories is not always helpful. Sometimes it actually creates more memory, larger memory. I'll show you some instances where it's worse. And this is what you need to keep cognizant of as you go through your data. So this is the interactive part. We can just follow along on here, but if you downloaded the code, you just go to that repo, cd, src, and then you can type Python int floats categories. So what this would do, it would produces 3 columns, an int, just a normal int, an int 8, I'm going to define it as an int 8, and then a float. And then the range of numbers is only going to be 1 to 4, and the length of the data frame is 10,000. So the top 10 rows, let's see if I can get so here's its index of the top 10, and then these are just randomly generated 1 to 4. So I'm getting the size of the data frame. So the int was a 1/10 of a megabyte. And int 8, it's a lot. It's a factor of 10 smaller. So I'm only going from 0 to 4. When Pandas reads in that integer, it's going to read it as an int 16 or int 32, not as an int 8. But by me defining it as an int 8, because I know I'm only max as 4, I drop the size of the data frame by a factor of 10. And the float is the same size as my integer. And then if I make these into categories, that int, if I make it into a category, which is an int 8, I drop the size of the memory down by 87%. But when I take that int 8 column, that's already an int 8, and make it into a category, I have some overhead for the category, so I increase the memory by like 2%.
So you can make a category out of something that wasn't a string column in the first place?
Right.
It's just probably dumb?
No, it isn't dumb. Because like that first column of integers,
Oh, I see, yes.
I dropped it down by like 87%. And then you can have like some really numbers, but the problem is if it's a, when we go to this random, that's not showing through. I thought I fixed this. When I go to the random, the floats, those never repeat. So now my data frame just increased in size.
So you have an index entry for each unique value.
Yes, and I have 10,000 values. So then that increases the size. So reducing, I'm going to reducing the frequency. So instead of having the range go from 4, like 1 to 4 random numbers, I'm going to increase it to 240. So it's the same setup as I had before, but so the range of numbers are going to be 1 to 240. The length is going to be 10,000. And then here are my values, my int. And I could see that it's still the same size as the data frame. But when I go to my categories, because now I have more values, is instead of like it reducing in size by 80%, I reduced it by 59%. And my int 8 category, because now I have 240 unique instead of 4, I just increased the memory size by 200%. So just, you just need to be cognizant, like, if it is already int 8, there's no point in making it into a category, especially if you have a lot of varying numbers, because you're just going to increase the size.
That talks to the memory footprint.
Yes.
Are you going to be talking also to, I'll call processing overhead as you talk, or as the function tries to convert each thing into a category?
It's really fast. Yeah, but you really don't notice it, even for really large data sets. And we're going to read in a 10 million line data set, and we're going to see the speed of converting things to a category, and then once it's a category, how fast can we retrieve? So we're going to have a data set where that's going to repeat the days of the week, and we're going to retrieve Sunday and see how fast that takes.
So would that speed also apply if you're trying to train a model on this data and you categorize the data?
Well, if you're trying to train a model, then you're just training, you just send them that category. Right. And then it probably would help you, because your model would have less overhead memory. And so then whenever you're not using every bit of RAM, things just run faster. So we're going to, now if I go from range from 1 to 4, but now I'm going to have 1 million lines. So just the same thing, but I'm increasing in the data set by a factor of 100. I could see, so this increased by a factor of 100. So I have, the int is a 7.6 megabyte. The int 8 is not even a megabyte, and the float is a 7. And you could see that we still have 87% savings. And since these are so large, it's in the noise. It's,
What is the data frame operating on? Is it operating on that float number, or is it operating on the 2 columns to the left?
The data frame contains a series for each one.
Yeah, this is the entire data frame.
You can think of a data frame as kind of like a
CSV cable.
Yeah. Okay.
Well, I guess I was right, but in terms of the categories, are you categorizing the in-column numbers, the int8 numbers, and the float numbers?
Yes.
Or just a subset?
No, I'm categorizing everything. So that 2 gets mapped to a number, and 2 gets mapped to a number, and the float 2.68 gets mapped to another number. And I'm doing each of those columns separately, and I'm looking at each of those columns, how much memory each of those columns is taking separately. So that you can see, but I mean, these 2 columns right here are basically the same. The only difference is that it's just randomly generated numbers. But it is, almost a factor of 10 difference in memory size. And so the best thing to do for this would be, reduce the as type to int 8 instead of what has a 32, int 32 what it is now. But when you have strings, that's when, like a lot of your data will have strings. You're going to have like either UUIDs or some sort of number, some sort of character. So I have this data set that I created. It's going to randomly create days, just repeat hello world. It fills in, repeats these locations like Beaver Creek, Oakwood, Huber heights. And then I'm going to create categories from those data sets. So days_C is a category. I already said it's a category. So the random strings, I'm going to have a random string of characters, 4 characters long. So just when you think of like 4 characters, like each character is a byte plus the overhead. So it's 4 bytes plus an overhead. And when I look at no categories, how much memory that takes is, 2 megabytes. When I look at with categories, it's 0.03 megabytes. And these aren't really nasty strings. These are just like regular strings. So that's where having categories, especially when you have strings, is really useful. So, and then when I look at the random strings, so you can see how the size of the memory. When I look at the random strings, when I did these strings, that 4 characters, and it's only 10,000 lines, when I converted it into a category, I almost doubled the size. That is like, yeah, that's not fun.
That's going to be dependent on the choice of random things that you pull.
I'm pulling the random the choice out of the alphabet. 26. The length is 26 characters. Now, when I increase the standard to 1,000,000 lines, so 10,000 lines, if you think about this, so 4 characters at 26, 26, 26, 26, 26, 26 times 26 is about 500,000. So with categories should help because I dropped the memory. I'm repeating, on average, I'm repeating twice. And so it is the same data set as you could see previously, but when I go look at the random categories, I drop the memory down. It's not as because there's overhead. Now, when we have a large data set of strings, so now it says that 4, I'm going to have a random of 6. I'm going to create 10 million lines. And this is going to create this string category Python. It's going to produce 2 CSVs. My awesome CSV, which is probably half a gigabyte. Both of them are about half a gigabyte. And then my awesome with categories, it's going to be just under, And I'm going to move ahead. So megabytes. Yeah, it's really. Yeah, because it's 10 million lines, and there's lots of categories, so 6 categories. And I have a random string of, 6 characters. So if I look at the data set, so this is a random string of 1 through 6 at the end, and 10 million lines, and this is like the top 10 rows. So with no categories, when I read in that half a gigabyte file, in memory, it's almost 2.5. It's 2.5 gigabytes. So it increased the size of the working from when it's at rest and when it's in memory by a factor of 5. And that's what you have to do, keep cognizant of, because when a language reads in your data, there's always an overhead for it, and it's with those strings. So that is the overhead that you're going to see right there. But when you use the categories, so you had half a gigabyte, now it's 28 megabytes. That's like almost a factor of 10. More, it's a factor of 20, and then that is pretty powerful right there. It's like magic. It's like I just freed up all this memory.
Well, that's why things like seeing a 256 megabyte level 3 cache. Trying to pick in a data set with 28 megabytes in it or 30 megabytes in it, the data, once it's sucked in, it's like all in high-speed RAM all the time, regardless of how it's being pinged then by your processor.
Well, yeah, when you read in the data, it's going to be in RAM, and that's where you want it because you want to process it, and especially for the speed. But you might not have the variability. The computer needs room. So if most computers that you have, like especially for Windows, it's only 16 gigabytes of RAM, and half of it is going to be used by the operating system. And if you are lucky, like whatever kind of, virus control software, you might be lucky that you have 8 gigabytes RAM available. And if you're using a third of it just for that data set, you don't have room to do anything. You don't have room to make a plot. You don't have room to make another data set. So this will allow you to drop it by, you're going from 2.6 gigabytes to 28 megabytes. That's huge. Now you have all this RAM available, so you can plot, you can stream music. And for me, I really need to stream my music to code. And if I had to, use up all my RAM just to read that data, I can't stream my music, and I become very unhappy. And now that random string, that's only one column. That random string, really, it was a bugger. It's like by itself it's 600 megabytes. And then when I convert that random string into a category, I just increased the size from 600 megabytes to almost a gigabyte. And so you do have to be careful because you can't use, categories when you have UUIDs that aren't repeating or any unique things. So just be very careful when you use it. So now we're let's read into that. We're going to read in first without using categories and then with categories. So we're going to read in my awesome, that the data set we created with categories, that's -c, that's one, that's going to tell it. And using some category, and we're going to use on categories that make sense. So we're not going to make categories on that random data set. We're going to use categories on the days, hello, locations, because those make sense, because those repeat. So before we read it in, and the memory of the data set is, 600 megabytes. And it took 12 seconds to read this in. So we're going to read in the data set with categories, already built in. And then and we're going to pull out Sunday. So we're going to read in without categories and then pull out how often Sunday occurs, and then with categories.
So I don't understand what you mean by categories already built into a CSV?
Well, when you read in the CSV, you can tell, so there's two options.
Oh, at read time.
Yeah, at read time, you could say, I want these to be categories, or you can do it after the fact.
By saving things as data frames then?
Well,
As a CSV file, if you have a CSV or JSON, whatever your data set is, like Pandas is tabular data, when you read it in, you could say, I want these columns to be read in as a data frame. And you can also set the data types too for each of the columns that you want. You can say,
You need to hand that off now to another program. You either have to reread that whole thing in, or you read in a data structure that's got the categories built into it so that you don't pick as much.
no, you don't. No.
a data frame is in memory by definition. Yeah, and if you're going to put it on disk or send it somewhere else, you have to
You got to
serialize it.
convert it back into something else.
Yeah.
And the beauty about Pandas, you can export it out in almost anything as like
Okay.
to CSV, to
My
latex, to...
understanding that when there's piles of data like that, R has a way to basically treat it as though it was an extended data frame on disk or in a file that has all these kinds of things tucked inside it, so that when it pulls it back in to do some kind of subsequent reprocessing, it only picks in the already compressed stuff, basically.
So you have a choice. You can like pickle data and save it off and as binary, so that if say you're processing it, there's all that stuff. But this is just about, you have a large data set, you want to read it in and play with it. And you want to read it in so that you have enough RAM that you can actually play with it and hopefully play music too.
So is there a concept of paging where you can get a chunk and then
Yes.
process
Yes.
and then write it?
Yeah.
Process, write it?
Yeah, and you could chunk the data in, and I haven't actually had to do that, but you can, because if it gets larger than like a couple of gigabytes, you really should do that and then chunk it in. But I did not know how to do that when I learned about categories, and then I was able to reduce the memory enough with the categories that I could like drop everything down. And one of the things, this data set what I had was super large, and when I read it in, I just said, ignore these columns because I don't want them, and so it won't. So you won't have to pull that data in memory. For these columns XYZ, call them an int 8. For these columns XYZ, make them into a float 32. For these columns, make these into categories. And I was able to, and then read it into memory. And you set that up in your read file. So it's like df, pd dot read csv, and then brackets. You could have this really long.
How does it deal with out of comments, structural elements like not a number or a missing?
It just skips it. It handles pandas, handles not a number, null. It handles mixed types. So your column could have integers and strings, characters.
Yeah, that's okay.
I imagine you'd have an exception file that you could create where you had something which there was a null or something that was a problem, and everything's boiled down to this, and you have to deal with those problem children.
And yeah, it's actually just one line. You can just go forward fill, back fill. You can do windowing, smoothing when you have missing data. You could have ignore. You can have delete, find. All of those are available once you read in the data. All that is all these one-liners that cleans up the data, but you still have to read it in. And so this is like, how do you read in this like really large data so that you can clean it up so you can process it?
So you work with this, you're working on the thing that you are preparing for. So it's not like a random file import. You have to craft this to that particular schema.
Yeah. To a certain extent, most of the time, if it's a brand new data set, I don't even know how it's delimited. I'm going to, grab it. I'm going to type in on my command line head and get the first 10 lines. So I could see, how it's delimited, what the columns are, and then I can read it in. Because usually you don't have that bizarre of a data set. But earlier in August, I was pulling NOAA CO2 data. And
not small data at all, right?
Yeah, it's for the last 40 years. And and it says it's a CSV. It's told me it's a CSV. Download CSV file. So I downloaded it. It's actually a text file. It's pretty space delimited. So it's not, and the spaces aren't consistent. And the first 40 lines were text.
Oh,
comments?
Of comments.
Verbiage.
Yes, but I could read that all in one line, because in Python Pandas had this beautiful thing for delimit by white space, not by tab, just white space, and then you could say skip the first 40 rows, and then boom, in one line I had this beautiful data set that I could process. So if you had ran the program of the data file, so it's a half a gigabyte at rest, and I'm reading in, I'm going to use, as I read it in, I'm going to use categories that make sense. So I'm only going to do the hello and not the random string at the end. And it would take about almost 8 seconds to read in, which is, not enough to drink a cup of coffee, but you could cool it down, but still pretty fast for, on a laptop. And it's almost a gigabyte of file, gigabyte in size. And the memory to data frame is now only 60 megabytes. So I went from it being at rest, 500 megabytes to 60 megabytes in RAM. That's with all the, overhead of having strings and the data frame. And that is beautiful. And I could do everything I want to. I could look at the categories. So I'm going to look at the days column. And if I look at the days column, it says it's a D-type category. And the category has 7 objects, which makes sense, because it's days of the week and it's 7 days of the week. And these are the categories. It's not in the proper order because it doesn't know about that, but I don't care about the order. I just want to make sure it has all 7 objects in it. And I could quickly see what those 7 objects are. And it took, I had this data set in memory, and it took half a second to pull out all the values of Sunday and get the index values of it. And that's, it is really fast and it's really nice. So I really like Python Pandas because the data sets that the previous program, like my CSV, creates, you can't read it in Excel. I mean, Excel just doesn't handle anything over 1 million lines. So this was 10 million lines and almost a half a gigabyte. And so, MATLAB can't read it in. Excel, Office Libre can't read it in. And we reduced the memory in RAM to less than the file sizes at rest, which is like, ooh. And you did see that sometimes categories can be hurtful, too. If you have unique identifiers and they don't repeat, making those unique identifiers, especially if it's a 16-character long unique identifier, making it into those categories will really, really hurt you, and it would blow up your data, the RAM, the size of your data in memory. So just use care. That's true with all our code. Just be careful. Think before you code. And this was my Hacktoberfest entry into Cloud Haiku. It's my prayer to Pilot. Is code, don't fail again. CI in the cloud, please take. Pilot, be my friend.
I don't recognize CI.
Continuous integration.
Okay.
So look, if you have continuous integration, usually there's code check to make sure code quality. And Pilot, I wrote this when I was having a lot of difficulty trying to get my code to be accepted by Pilot.
A lot of code bases are set up so that when you're trying to check code in, it runs Pilot against it and it's perfectly likely to say, yeah.
Yeah.
So you will probably say this prayer a couple of times.